Well, good morning. So, for now, let's pretend it's still yesterday and finish this conversation because it hasn't been finished in a rush. And this is all about how we measure angles, nothing else. An angle has been defined as a space between two lines or two directions. Well, if you have two directions, you need to extend those directions to make lines so they would cross. That's the first step. And second step, measure. Well, technically we have two measures, but normally we use the smallest one. And the smallest angle between two directions always lies between 0 and 180, nothing else possible. And if you take a calculator and calculate the values of cosine for different angles, you get 1, some positive to 0, and after that they go negative. So depending on the angle, this particular combination of variables which has a name, magnetic flux, can be anything. Positive, negative, 0. This is the question I want you to ask. This is a bar magnet which has a specific orientation and maybe is at rest, maybe in a motion. It doesn't really matter. And there is a coil, loop, solenoid. Yeah. Loop and coil normally, well, a loop is one winding, solenoid many, and coil people, well, when people say coil, they sometimes means loop, sometimes means solenoid. It doesn't really matter to us. So that's what is happening. And using the definition we just have refreshed, we can make a statement, a definite statement about the magnetic flux of the magnetic field of that magnet at the location of the loop. So you please keep answering. It's not should be happening here, it should be happening in this space in your paper without drawing. You can't make sure that your answer is correct. Now, I just want to use this time while you're thinking and entering to review what we've talked about a ball in PY 105. A tennis ball. What can you take? What can you tell? What can you say about it? Lots of things. Yellow, small, soft, fuzzy, cheap, but memorable. And we can go and go and go. The list is long. Same process should be happening with everything we talk about in physics. Bar magnet. What can we say about bar magnet? Some properties, issues, features related to this particular object. Name one. Two poles. What else can we say about bar magnet? Solid, loud. What else?
It
right? So what do you think is more important? That it generates magnetic field, or that it's cold? That it generates magnetic field. So every time when we name something, we should experience a rise of many, many different words, terms related to this subject, and then we should select which could have been more important for this particular situation. For example, if we don't care about affecting compasses, but really need to hit someone or something, the fact that it's solid will be more important than the fact that it makes compass turn. This is what physics is about. That's what we call properties. Property of a magnet, property of a process, property of a loop, property of a magnetic field. Everything has lots of stuff which just has to be a part of our memory. And then we can make a connection between those two. So here, survey says at least 10 more answers supposed to be reflected. I can see more than 28 people. Everybody said something? Is it really 28? Is my vision again fails me? Now we can see a clear winner, yeah? The answer number 3. Oops. Oops. Now I'm sounding like Rick Perry in the debates. Well, you don't know probably who's Rick Perry. Former governor of Texas who wanted to be a president, but he didn't become a president because of this word. Oops. You can look it up. Anyway, so first of all, bar magnet generates magnetic field. How do we demonstrate the presence of magnetic field in space? South, north. What should we draw? Lines. Yeah, we call them lines. Specific lines, magnetic lines. We know magnetic lines are loops, so not like electric field lines. These don't have any end and beginning. They look like this, or like this. They are everywhere, inside and outside, but they also have direction, and we need to know the rule about it. That rule, as any rule, doesn't require understanding or thinking or reasoning. It's a part of knowledge. How should we draw an arrow which represents magnetic field at the location of this magnet? What's the rule? Where? The bar magnet divides the whole space in two regions, inside and outside. So when we say a rule, we have to say it completely. It has to point from to there. So the rule says from south to north inside the magnet. If you don't say the whole rule, you may make a mistake. Maybe not, but who knows? So, and outside they go away from north because it's very cold there. These are magnetic field lines of a bar magnet. But the loop is here. We cannot say anything about anything related to the loop yet because we don't see lines traveling through the loop. So what do we do? We have to use our imagination and extend those lines. don't lie. So this one goes very, very, very far away and disappears. It doesn't mean it doesn't exist anymore, but eventually it comes back into the South Pole. Any questions on that? So right here, right now, the magnetic field vector should point like this. That magnetic field vector, that's the area vector. So now we can look at the angle. Well, technically, we have to redraw two vectors so they would begin from the same point, because that is a part of operation we call measuring angles. That's the angle we need to measure. Now we can apply, well, the definition of that thing we are looking for. Now, this variable flux, capital Phi, is related to two magnitudes, and we don't really draw those vertical bars anymore every time. But this is the actual value of this function. So if you look at this picture, for example, this angle is about, again, 120 degrees. And we know that cosine of 120 is negative. Well, for 120 degrees, it's actually exactly negative half. So the answer is 3, negative. That is correct. But of course, it's not just about being correct. It's about being able to prove it. Well, in my example, I used a different line, which is almost horizontal, closer to 180, but still negative. Now, we saw this picture. It is a representation of our thought experiment with a loop, conductive loop, traveling in non-uniform magnetic field. And when a charge traveling in magnetic field, Lorenz's force makes in this situation makes it move, because the net force acting on electrons is not zero, and because of that we observe electric current. So now we have to make one more step when electric current is being generated in a loop. Electric current generates its own magnetic field. So there are several steps of action in this phenomenon. Magnetic field, loop, magnetic flux inside the loop changes because of some reason in our experiment, because we've been moving the loop, but technically it doesn't really matter why magnetic flux changes. As long as magnetic flux changes, the number of magnetic field lines inside the loop changes. We observe electric current in the loop, but that electric current also induces another magnetic field. So to separate those magnetic fields, the first one we call the external, and that we call induced. This is the induced current induced in the loop or coil, and the induced current induces induced magnetic field. And that completes the chain of actions. Now we can complete this sentence. A bar traveling in magnetic field starts acting like a battery. That's it. Unless we connect it to something else. And that actually would make it a loop. And the loop, in changing magnetic field, starts acting like a circuit with a battery. And as a result of that, it also induces its own magnetic field. And the question, in our specific experiment, what's supposed to be the direction of the magnetic field induced by the current, induced by the change of magnetic flux inside the loop? For a moment, I'm going to switch to the browser, and I'll come back. And in a moment, I'm going to see it again. So you may think, what do I do right now? I'm fighting for the new room for the exam. So what's more important, this or that? All right, I want to see what you said. One more time. Clear division 1224. We've lost 3 people from 39 to 36. Well, this arrow tells that the current should travel clockwise, and this picture says clockwise means into the screen. So if you said something different, you should ask yourself, why? It's a very important question. Because the answers are right there. And yes, it's supposed to be, well, again, yes, this is the right-hand rule number 5, electric current, magnetic field. In the past, and in a different country, people call this rule not the right-hand rule, but a corkscrew rule, because it works exactly the same way. If you take a corkscrew, if you start it, rotate clockwise, the tip of the corkscrew will move away from you, counterclockwise toward you. So I don't know what's you like more. Corkscrew rule, right-hand rule, essentially it doesn't matter. You had a question.
Why is the directional current point?
Do you see that big red arrow? That's why. Well, this arrow has been proved by applying the Lorenz's force to electrons inside the loop yesterday. And today we're going to talk about a slightly different approach. Right now, this is just a fact. If you look inside the loop traveling in magnetic field and try to calculate Lorenz's force acting on electrons, it's not zero. There is net force which makes them rotate in this direction. But first, we need to, at this very point, we just need to use it as a fact. And this picture technically explains all possible situations. If we take this as a fact, what can be changed? What can be different? Well, instead of magnetic field pointing like this, magnetic field could point like that. That's one possible difference. What else can be different? Well, instead of having more and more magnetic field lines, we may have less and less magnetic field lines. That's another possible change. So if we make one change in the process, that should make one change in the result. So for example, if magnetic field would point into the screen, so we would have to flip the direction of electric current. Technically, we have solved all possible problems, and there aren't many, only 4 situations. only from this perspective, magnetic field might point away from you into the screen, and magnetic flux might increase or decrease in magnitude, so more lines or less. Or magnetic field might point out of the screen, and again, magnetic flux, number of lines, might increase or decrease, only 4 options. So we only have 4 results. This is the result we've talked about initially. This is our experiment. But so you can just memorize 4 pictures. Or we can make a next step and talk about a very fascinating thing we called Lenz's Law. First of all, again, this sequence demonstrates kind of what's happening in general in a situation like that. We need magnetic flux change. If there is no change, nothing will happen inside the loop. But if flux changes, first of all, Michael Faraday have proved that the rate of change of flux is equal to EMF induced in a single loop. If we have many loops, so we just have to multiply by the number of loops. Now, the change of the magnetic flux results in the generating, well, again, new kind of electric field, which results in creating electromotive force of new kind, not chemicals, new kind of electromotive force, but still the same electromotive force divided by the resistance of this circuit will be equal to the electric current generated in this circuit. And this electric current generates its own magnetic field according to the right-hand rule. So this is the sequence of the events. And so far we have to use vertical bars. So far we only talk about magnitude of EMF induced. And technically, it's not the instantaneous value, it's an average. If flux changes from one number to another, yeah, like distance over time is average speed. For the instantaneous value, we can use the analogy from PY105, and we will right now. We've done some graphics in PY105, velocity, position as a function of time, acceleration, and mathematically there is no difference between calculating delta x over delta t or delta phi over delta t. It's just a different letter. So all that knowledge from PY105 about a relationship between position, time, velocity can be used here. In particular, if we have a complicated graph for position as a function of time, the slope of that graph represents velocity. So here we can just immediately use this analogy. Instantaneous value of the graph, instantaneous value of EMF related to the graph of the flux as a function of time. And this minus will be explained very soon. So this is our classical experiment. We always keep in mind something like that. Just we saw it yesterday, so just let's see it one more time. A magnet travels through, and we can see when it moves, we observe the deflection, which means there is EMF induced. It starts acting like a battery, and that battery generates electric current in a closed circuit. And our initial experiment looked like this. Static magnet, moving coil. We still observe the EMF induced in it. And we explained this experiment by the force acting on the electrons. But if we try to explain this experiment using force, that wouldn't be possible. the Lorenz's force wouldn't act, but in this situation, the changing magnetic field creates electric field, which starts acting on electrons, and force from electric field on each electron equals Q times E, and that makes them move, and we can see electric current travels. Now, classical experiment might look like this. So don't be deflected by the sound. The sound is not a part of the experiment. The experiment is happening when the magnet travels through, and you should look at this. Well, I'll try to make it softer. Although in the morning, loud sounds help. So, does it move? Did it move? Moved. So what is happening? Well, we can imagine that it starts from very far away, moving from very far away. So in that situation, there is practically no magnetic field at the location of the coil. Then magnet gets closer and closer and closer and closer. So stronger and stronger magnetic field is generated at the location of the coil. And when the magnet is inside the coil, we observe, well, the flux reaches maximum. And then it's leaving the coil, and the magnetic field eventually goes again practically to zero. That's what's happening. And to describe this mathematically, we will need to use this equation. So let's sketch. I'm going to give you a minute. Try to do your own sketch first. So this is the experiment you just observed. Solenoid, falling magnet, and we are told to choose the area vector up. Since technically, at least at this point, we don't know what will be the direction of the current. So we just choose the area vector wherever we want to. If we knew the exact direction of electric current, we would choose area vector according to the right-hand rule. That's just a matter of tradition, convenience. But in this situation, we don't know yet what would be the direction of electric current. So the area vector points up, and this is the equation for the flux. First, you should add magnetic field lines to your picture, so we know they should travel how? Anyone? I don't see you. How? Like this? So you see, you gave me wrong instructions. I literally followed what you said. So now, how should I draw magnetic field lines? Anyone, feel free. You can say anything. Outside of the magnet from north to south. Yeah, some are short like this, but some should be long, and eventually they go away. But eventually, again, they come back. That's it. That's one line. That another one. And technically, magnetic field changes horizontally, yeah, from point to point. But with it doesn't affect the graph. We can just make a little change. We can say B average. Yeah. Somewhere here. Now, area vector. How should we point it up? Well, how do we know? First, we can read, and second, we know what up means. That's the area vector. So initially, we assume the magnet is very, very far away. If the magnet is very, very far away, and we know that the magnetic field strength is proportional to 1 over the distance. When the distance is huge, that should be practically 0. And if we multiply by 0, we should start from 0. So now, when it's getting closer and closer, well, of course, the area remains constant, same. And for the average value of magnetic field, which looks like this, B average, and the area vector, we're always going to see the same angle, which is what? What is the angle between the area vector and the magnetic field, the average magnetic field? The green arrow and the blue one. Do you see it? I see it here, but it might not be clear on the screen. I'm not sure. 180. And cosine of 180 is -1. So, well, this is at least for now. At least for now. So it should go into region of negative numbers. But when the magnet is right inside the coil, we should have the strongest magnetic field, maximum flux should be reached, and after that the magnet is leaving the coil, and eventually the magnetic field strength goes back to 0. That should be kind of a sketch of for the flux as a function of time for this particular situation. Now, so what should we observe here? Well, again, technically we cannot use this because that's the average. However, if we try to take a look at two very close instances when delta t is practically 0, yes?
On the picture before, why when it was coming out of the coil did A point downward?
Oops. Again. Just a second. In that case, I'm going to need to be saved. I'm going to need to add one blank slide first. Maybe not. Okay. You just have to draw the picture. Why are you asking me? You should ask yourself with the new picture. So technically we have 3 situations to discuss, and north, 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 south, south, south. And in all situations, so I'll try to use, so this is case number 1. Inside, case number 2. And now you have to draw the magnetic field lines, at least one, for the magnet when it's below, but the magnetic field line of that magnet should travel through that coil. How do you draw it? You have to apply the same rule. That's supposed to be the magnetic field line. And for all three cases, we can see that the orientation for at least average magnetic field is the same. Down, 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 up, up, up. Doesn't have to be 180, could be 170, 160, still will give a negative cosine.
At the bottom of the spiral, an arrow pointing downwards with A.
I didn't erase anything.
The one that the slide lost, at the bottom of that coil, you had drawn an arrow down with A.
And that arrow represents everything has gone. All right. So next week, I'm going to go back to the jittery screen. I prefer have the screen jitter than losing my handwriting. It's always a choice between bad and worse.
If you wanted to maximize flux here, you just flip the orientation of the magnet, just so it's passing through the.
Can't hear you.
If you
Is
want to
this-
maximize the flux, you just flip the orientation of the magnet to the south pole.
The maximum of the flux means it reaches the magnitude, the critical value of the magnitude, which can be beaten. Nothing is greater than that. It's not about orientation. It is about the magnitude. This is when the flux reaches maximum. This is the physical term. Maximum even if mathematically it looks like a minimum on a function, which requires calculus, which is outside of this course. So maximum.
That's a decrease in flux. That's the maximum decrease in flux that can be achieved. Flip the battery, you'd have the maximum increase in flux.
Okay, this is the mathematical discussion. Depends what do you call decrease or increase. So if you go from -5 to -10, do you call it increase? You call it decrease. So that's what I said. Mathematically, this function is increasing and reaching mathematical minimum, but physically, the flux reaches maximum magnitude. That's what this means. And magnitude is never negative. So you want to sketch the, if you want to talk about what's happening to the magnitude, you have to sketch the graph for the magnitude. So this is when we say flux reaches maximum.
But let's say we were talking about one of those Lenz's Law problems.
We don't talk about Lenz's Law problems.
We were talking about
Well, we don't talk about Lenz's Law problems
talk about
because you're stopping me and dragging the class down.
I'm trying to ask a question.
Oh, you asked the question and I answered the question. And now you're asking a different question and I don't want to ask, I don't want to talk that question yet because I know what happened, what's going to happen, and you don't. That's it. We're going to talk about Lenz's rule. So if I will not answer that question in several slides, come back and ask again. Just remember it. So this is a difference. It's Friday, lecture 13. just facts. So I'm going to put it back. So again, when we say, this is a terminology physical, not mathematical, when we say flux reaches maximum, we mean magnitude. And this is the instant when we say, at this instant, T equals M of flux, the flux reaches maximum magnitude. That's what we say. Now, here, going back to your question, this is the same arrow I had inside the coil. That's the same arrow, blue arrow there, which is average magnetic field, and the same arrow is just now outside of the coil.
That I understand. Just before it had an A pointing down. Now I understand.
No, I've never had A pointing down. And I can prove it. But for that, we have to stop, wait for the movie. Now, next part is about instantaneous, because so far we talk about algebra, and in this situation, this is what we should say. It will eventually become equal to the magnitude, so far magnitude of the slope. That's how it changes. So we just have to look at what's happening to the slope. And that's actually a handy exercise. Slope as a function of time. And in mathematics and in physics, there is no difference here. Negative slope, negative, negative. So almost zero, more and more negative. And there is some critical point here, and after that it becomes more and more horizontal. Horizontal here, and then from here becomes more and more steep, but after a certain point becomes less and less steep, more and more horizontal. And horizontal line has no slope. The slope for the horizontal is 0. So we practically start from 0, and we go to 0 again, and we go to 0 again, and in between we should have 2 peaks. But since so at first it's going to be negative, and then it's going to be positive. That's how it should look like. And now we just have to connect, you know. Don't really have to do it very accurately, that's it. But now, magnitude of that makes it positive. Things which used to be negative become positive, things which used to be positive remain positive. And now we can see that no matter what we draw, slope or magnitude of it, we have 2 peaks for the EMF. So magnitude of EMX reaches maximum twice. Where? Well, somewhere here and somewhere here. T1, T2. Those are critical times. But if you look in, if you remember our picture, this instant is related to a case when the magnet is completely in the coil. So when the magnet is completely in the coil, the EMF actually is 0. EMF reaches maximum when the magnet is somewhere before or after the coil. So people sometimes confuse maximum flux. Oh, it's not aluminum. I didn't know that. Maximum flux and maximum EMF. They reached at different times. This is the most important conclusion. Maximum for EMF and maximum for flux, different in time, reached at different times. Now we're going to talk about Lenz's law. Lenz's law tells us how to relate the process happening inside the loop with the final direction of electric current induced by the changing magnetic field. And again, we have two equally convenient options. We can memorize 4 situations, nothing else possible. Or we can follow, actually, let me check. Okay, so if I draw it twice, it's safe. All right, so we can just memorize 4 possible situations, nothing else might happen. So this is the one we used to have as the mean. Or we can use the Lenz's law. The Lenz's law says that this flux induced by the induced current should oppose the change happening to the external magnetic field. That's what it says. So, and this is a rule, which means it doesn't require thinking or reasoning. It requires literal memorizing. The induced magnetic field should oppose changes happening to the external magnetic field. That's it. What does it mean? That requires some thinking, but mostly practicing. So now this slide is just a review of everything we've said about this particular phenomenon: Faraday's law, Lenz's law, all equations, a particular example from which we can extract 3 more, the relationships, the Lenz's law. So please tell me what you think now. So for this experiment, select the area vector of the loops down and sketch the graph for EMF as a function of time. So that's going to be on the next slide, but the question is, what magnetic flux at the location of the coil as a function of time looks like? This is always a middle step. Eventually, of course, we always talk about EMF or electric current, because EMF over R is electric current. But we cannot say anything about EMF until we say something about flux. So you should say something about flux in this particular experiment. It is time to say something about flux. That's a question number 4. Again, if every piece of information you need to know to answer the question is available, so you just use it and answer the question. If you think some information might be missing, you should ask an additional question. It's always up to you, it's your choice. And we're starting seeing distribution. And if the question is about flux, we need to draw 2 arrows. One arrow is supposed to represent the area vector, second arrow is supposed to represent magnetic field. So how should I draw the area vector? what is the direction of area vector? My microphone works? Can you hear me? This experiment select the area vector of the loops down. So what should I draw for area vector? And what is the direction of the magnetic field, let's say, for that particular instant with the magnet above, but the magnetic field is supposed to be at the location of the loop, inside the loop. What should I draw? How should I draw B? Down, because nothing changed physically. It's same coil, same magnet, same magnetic field, so still down. Same exact reasoning as before. But now, with the change of the choice of the area vector, the angle changed, right? That's it. That's the only difference. At first, we're going to do flux. And the flux now, B average area cosine theta, should remain positive. So you see, it's exactly the same coil, it is exactly the same magnet, it is exactly the same process, but mathematically the graph is different, which means it is actually up to us. By choosing the area vector up or down, we can make the graph look the way we want to, if we want to. It's just, you know, the nature doesn't have area vectors. It's all in our mind. So it's all the way we look at it. And the way we look at things, changeable, we can change it. But now, how would we draw the graph for the EMF? Actually, I'm going to add an extra slide. So first, I'm going to go, okay. Okay. So it is always about the graph which represents the flux as a function of time. Then, as a mean of practice, you can draw the graph for the slope. So what's happening to the slope? Almost zero, positive, positive, and then goes back to zero. So the slope starts from zero, goes back to zero, remains positive, supposed to reach a peak value. And here goes to zero, but should be negative, supposed to reach the peak value, negative. But, so we saw an equation, we don't know why, and soon we will. Actually, we know. I just didn't say it out loud. That word oppose, which was a part of the Lenz Law, makes this to be negative. Yes. And if in general, if we have many loops, yeah, just in case. It doesn't affect the graph at all because it's always a positive number, 1 or 500. So because it's negative, we just have to flip the whole graph of the slope. That will be the graph for EMF. Now, electric current is equal to EMF over resistance, and the R is always positive, N is always positive. So N is the number of windings. So if we want to plot a graph like that, the shape of this graph should be equal to the shape of graph for EMF. It might be just skewed vertically because we're dividing by positive number. Now we're going to solve specific problem applying Lenz's law and Faraday's law. In this situation, we have a loop of wire. Well, that makes things tricky when we read a problem and it says page. Yeah. If you have your notebook on the table, for you, it's going to represent a horizontal surface, but for the screen, the same loop would be vertical. And that makes people confused sometimes. So it has certain dimensions, resistance, a uniform magnetic field through the loop points into the page or into the screen and increases from 0 to 1 Tesla in 10 seconds, so which means changes. So we have to calculate electric current, we have to describe the direction of induced current, induced magnetic field, and we start from direction. So now this is a method, a sequence of steps, the algorithm, which we should follow if we need to apply the Lenz law. We call it before, after, to oppose. BAO, before, after, to oppose. We have to draw pictures. The first picture we call before. Before something happened. We take a snapshot of a situation, like this, for example. Then we imagine we wait some seconds, so something should happen. Maybe the magnet moves, maybe the coil moves, maybe magnetic field changes, coil turns. That if the coil turns in magnetic field, that changes the angle. So doesn't matter how we made the change, but we have to draw the picture which represents the state of a system after change happened. Then we have to make a call. How do we call that change? And the magnetic flux might, well, technically, magnetic flux might remain constant, rare situation, so no change. But if change did happen, magnetic flux might increase or increase in magnitude. If magnetic flux increases in magnitude, we call the change an increase. And then we have to say that the induced magnetic field is supposed to oppose the change happening to the external magnetic field. This sentence is supposed to be converted into a single arrow, which represents the direction of the induced magnetic field. And then we can apply the right-hand rule to relate the direction of the induced magnetic field and induced current. So, step number one. Well, first we need to draw the loop. It doesn't say if it's a circular or rectangular. In the problem it was rectangular, so we can do rectangular, circular, triangular. It doesn't affect the method. Now, magnetic field initially points into the page, and that's it. We see the loop, we clearly see some magnetic field and direction of magnetic field. Done with this picture. So now we have to draw the picture we call after. Same loop, magnetic field still points into the page. Now we have to make a statement about the number of magnetic field lines inside the loop. Should I keep the same number? Should I decrease that number? Or should I increase that number? What do you say? Increase. We told so. So we just have to add some more crosses. Yeah. An increase. Done with this picture. Now, to oppose. This is a question where people sometimes get confused. What should picture to oppose, show opposing. That doesn't require thinking. It requires memorizing. It says it's a part of a rule. It opposes change. So, not magnetic field. The change happening to the magnetic field. All right, we are clear on that. Now, what is the name of the change? How do we call this particular change? An increase. I do that. Now, we should say something about the induced magnetic field to oppose the change happening to the external magnetic field, which we know. An increase, how the induced magnetic field should point. And we have only two options. Same as external or opposite to it. If we want to oppose, slow down an increase, to oppose meaning slow down, this is the presence of inertia in electromagnetic phenomena. Nothing happens instantly. Everything takes time because there is inertia. To oppose an increase, the induced magnetic field, how should it point? What do you say? Opposite to the external magnetic field, that's the logic, yes. So, to oppose an increase, the induced magnetic field should be opposite. So this is the rule, which I think is very natural. To oppose an increase, the induced magnetic field should oppose the field, but to oppose the decrease, the induced magnetic field should support the field, which means parallel or anti-parallel. We always, well, again, have to make a choice only between these two options. So in this situation, we said that the induced magnetic field should point opposite to the external. Now, this word opposite to the, well, sentence, statement, opposite to the external has to be converted into one single word, in or out. Are you in or you're out? What do you say? Exactly. If induced magnetic field, in this particular case, should oppose direction in the screen, that means the induced magnetic field should be pointing out of the screen. That's how we eliminating wrong answers step by step until we get the right answer. Now, this symbol represents the result of the Lenz's law. Well, we still have to make one more step. You should tell me now, in order to induce magnetic field directed out of the screen, how should electric current inducing this field be directed? And that will complete the sequence. That will complete the algorithm. So you have to enter this is the right hand rule number, I don't know, 5 or 6, right? So what do you say? Clockwise or counterclockwise? Counterclockwise, yep. That's it. We are done with Lenz's law applied for this situation. Counterclockwise, that's how it works, step by step. This is a specific case, but the rule, of course, can be applied to all possible situations. So keep in mind that word to oppose means oppose the change, not magnetic field. And These are the steps we just went through. Yeah. And again, no matter what's happening, we always come back to one of these four situations. But now we can also say that we could apply the same rule backwards. Let's say we know that the induced magnetic field points up, and the question is, how could it be done? Well, in this situation, we have only two options. The external magnetic field might point opposite and get stronger and stronger, or the external magnetic field might point in the same direction, but getting weaker and weaker. And now we just need to finish calculation. So we have to calculate electric current. The electric current, of course, is given by the Ohm's law, right? And we know the resistance, which means automatically all we need is EMF. And again, just to practice, we can start from the graph for the flux as a function of time. The equation is BA cosine theta. Now. Magnetic field points, external magnetic field points into the screen, and that's what we're calculating. But the induced magnetic field points out of the screen, and it's just again a matter of convention. If we know the direction of induced magnetic field, we choose the area vector in the direction of the induced magnetic field. That's it. So this is my loop. I choose the area vector out of the screen. My external magnetic field points into the screen. That makes this angle to be equal 180 degrees, wherever. Just a number. So the magnetic flux will be equal to magnitude of field times magnitude of area times -1. Now, field starts from 0 to 1. So flux starts from 0 to F final is equal to 1 times area. Area is, so this is 1 meter. This is a half of a meter. 1 times 1/2, -1. Well, in 10 seconds, that 10 seconds period, in 10 seconds, the flux will be equal to -0.5, that's what we call Webers. And that will be the graph. Straight line, which means EMF will be constant. EMF will be equal to -1 times the slope. Or we could have used just the average. In this situation, there is no difference between instantaneous and average. So here, hence, it actually will be positive anyway, because if the flux is negative and we multiply it by -1, it automatically makes EMF positive. So it's going to be one loop times 0.5 minus 0 over 10. So that gives 0.05 volts. And now we can use this number here. 0.05 over 0.1, a half of amp. So this problem is a very typical example of a combination of Faraday's law equations and Lenz's law. If we don't care about the direction, and we don't care about the direction if we're not asked about the direction, we don't have to use the Lenz's law at all. We can just use the Faraday's law and calculate the magnitude of the EMF. Now, I want to switch back and forth and see if you have to use your long-term memory. All right, question. Not a question for you, just for us together as an additional example of application of the Lenz's law. Here we don't have any calculation to do. We just have to apply the pictorial method before, after to oppose, BAO. What's happening? Well, first of all, a note about a multimeter or galvanometer. See, I can connect it like this. I can take a magnet and I can move the magnet in, and we can see the deflection is to the left. But if I forgot, what was it? Okay. Just reconnect the wires, it will be to the right. So to check if either wire is connected in the proper way, we always can take a battery and connect a positive electrode of a battery to a plus, a negative to a minus, and a properly designed multimeter should move the arm to the right. That's what it says here. What does it tell us? It tells us that if the properly connected coil makes this needle move to the right, that means electric current should travel into the positive electrode of the multimeter. That's it. That's how we relate it. That's it. So right here, we use the proper multimeter. And now we need to make a prediction what should happen to the multimeter when electric current in that wire traveling like this increases in magnitude. That's the goal. So you should do what I do. You should draw pictures before, after to oppose. So before, after to oppose. Right now, in a picture at this instant, what is the direction of magnetic field of that wire in the loop? Magnetic field is everywhere, but we don't care about everywhere. We only care about that particular instant and that particular location. Here, how does magnetic field point? Up, down, left, right, out of the screen, into the screen. What do you say? What do you say? What do you say? So current, wire, right-hand rule into the screen. What about this? Doesn't matter. Current into the screen. Right-hand rule relates direction of a current and direction of magnetic field into the screen. Into the screen. Now, magnetic field is related to electric current. If electric current increases its magnitude, magnetic field increases the magnitude. The flux is related to magnetic field. If magnetic field increases, flux increases. So after we wait for a while, we should have more magnetic field lines, which means this is exactly the same situation physically as we just have solved. This change has a name, an increase. And to oppose the increase, the increase of external magnetic field, the induced magnetic field should be opposite that the induced magnetic field. And now right-hand rule says again, electric current should be counterclockwise. Done. Same but faster. Deflection. So if electric current here travels like this, be induced out. If electric current travels like this, so like this means it travels into the positive electrode, and traveling into the positive electrode means the deflection should be to the right. That's the answer. Let's say we have a loop traveling through magnetic field. So we have several cases here in one. One, when the loop is outside of the magnetic field. Two, when the loop is entering magnetic field. Three, when the loop is traveling through magnetic field, etc., etc., etc. Here, for the case number one, should we have any EMF induced in the loop? No. B is just 0. So nothing is being induced. Here, the case number two, should we have EMF induced? Yes. Here we can actually draw pictures before, after to oppose. So my snapshot shows me some magnetic field, but if the loop getting deeper, we get more magnetic field, which means automatically picture to oppose again should be the same as just before. Induced magnetic field, induced electric current. Case number three. It is traveling in magnetic field. What should you say? What do you think should you say about EMF? Well, actually, pictures before and after help. Let's say it's right here, right now. So we have like, and we wait a little bit longer, we still have same amount of flux. So magnetic field is not 0, flux is not 0, but flux doesn't change, remains constant, which means there is no change in flux, which means there is no EMF induced. Now, we also have, for a rectangular loop, we also have a different approach to figure out what's happening to EMF. Because a rectangular loop is just a combination of 4 bars. And for each bar traveling in magnetic field, there is motional EMF. It starts acting like a battery. And the battery is responsible for electric current. So there is a relationship between the motional EMF and Faraday's law, very simple. We can look at EMF induced in each side of this square loop. Magnetic field, loop. So first of all, this is velocity, this is magnetic field. For motional EMF to be induced, all 3 directions must be must have perpendicular component. This side is parallel to velocity. This side is parallel to velocity, always. So there is no EMF induced here or there, no. EMF only can be induced in here or in here. That's it. And, well, we know how. Yeah. This bar is entering magnetic field. Magnetic field is into the screen. So how would electron move? Or how would fictional positive charges move? Positive charges would move there, electrons here, plus, minus. Example we've done 2 days ago. That would make this battery, make current travel counterclockwise. That's it. In this situation, both sides become batteries and they cancel each other out. Now here, it travels through the boundary between the region with magnetic field into the screen and out of the screen. We have EMF induced here and here, but now they're not opposite. Now they're actually in the same direction. So they induce twice of EMF, twice of the current. So we always have more approaches, more ways, which is good. We always can check. They should match. If you use Faraday's law, Lenz's law, or Motional Emf, the result always have to be the same. This experiment. Well, again, we have done it already like 3 times. Magnetic field points like this. And the average magnetic field always will be directed straight down. We only have to choose the direction of the area vector if we want to plot the graphs. But if we don't care about graphs, if we only care about pictures before, after, to oppose, the area vector doesn't matter. Area vector gives angle, mathematical entity. Pictures only show directions. And to draw exact directions, we have to make a very important choice. How do we look at it? We can look at it from above. That's an eye. Or we can look at it from below. And the perspective makes difference. Because if I look from above, this is what I see. I see a coil, and I see magnetic field lines away from me. That would mean into the page. From above. But if I look at at exactly the same situation from below, this is my eye, and magnetic field lines now point at me, and I use my imagination to see that. If I don't have my imagination, that's it. Physics is done for me. And this is what I would see. Magnetic field lines would point at me. So, of course, we don't have to do both. We have to make a choice and just follow the choice. From, again, for the first part of the motion, time number 1, time number 2, magnetic flux increases. And so increases more lines here, or more dots here. And that means for this part of the motion, that's only a half of experiment. For this part of the motion, the induced magnetic field should oppose the change, which means like this, again and again and again. However, in this situation, from the perspective of a person looking down, to oppose would mean this. And for that person, electric current would have been clockwise. This example should tell us that we have to make a statement about the point of view, how we look at it. And we cannot change it, because if we change it in the middle of the process, all pictures, well, not all, but some of the pictures might become wrong. So we have to make a choice. How should we look at it, or how do we look at it, and stick to that choice until very end. Now, so what do we need the area vector for the graphs if we need to plot the graph? And we did that before. If we choose the area vector up, that makes flux in this situation negative. If we choose the area vector down, that makes the flux in this situation positive. But the behavior will be the same. Flux goes from 0, reaches maximum magnitude, goes back to 0. EMF goes from 0, reaches maximum, goes to 0, reaches an opposite maximum. So for the area vector up, area vector flux. So this picture, no need to have a vector. This picture, we need to choose the area vector. That's the difference. Now, sketch the graph for the EMF for the previous graph. I can again, because I know some of the writings will be lost, so let's do it one more time. For the previously sketched graph, EMF is equal to negative positive number times slope of the flux. Starts from 0. This is where it should reach maximum. The slope is negative, maximum is positive. 0 again, should be next, up it first. For the current, always preserves the shape of the graph for the EMF, because we just take any number for EMF and divide by a positive number. By a positive number. So, one more thing. This is some information from PY 105. This is the easiest example when speed is constant. So, if we use this equation backward, solve it for the displacement, it only means I have 1 more minute left. So the fact which we're going to use on the next slide is that the area of this graph will be equal to the delta x, the displacement. But exactly the same mathematics, as we said, can be used for EMF and flux. So if we have the graph for EMF, this area will be equal to the difference between initial flux and final flux. And now we're done. Thank you very much. Have a nice weekend. Do your homework. Send questions, post questions on Piazza.